Let's take another look at Kirchhoff's voltage law for advanced circuits, including more than one voltage source. Consider the series circuit consisting of E1, a 16-volt source oriented positive to negative, top to bottom. R1, a 40-ohm resistor. E2, a 7-volt source configured positive to negative, left to right. R2, a 70-ohm resistor. E3, a 15-volt source configured positive to negative, top to bottom. R3, a 50-ohm resistor. And finally, R4, a 60-ohm resistor. There's really no practical use for this circuit besides an excellent means of putting your understanding of Kirchhoff's voltage law to the test. If you're up to the challenge, feel free to tackle this one on your own, but if not, follow along. As you are no doubt aware, Kirchhoff's voltage law states that for any closed loop, the summation of voltage rises will be equal to the summation of voltage drops. In summary, what comes up must come down. Where to begin? There's like 3 voltage sources of different magnitudes in this circuit, and they're all pointing in different weird directions. Some relationships might be aiding, some might be opposing. However, if you stared at this circuit long enough, you'd realize that sources inducing current in the counterclockwise direction kind of gang up and seem to dominate the show. The 7-volt and the 15-volt source join forces and overwhelm the 16-volt source such that current would flow counterclockwise. Given counterclockwise current, the polarity of the voltage drops across the passive elements in this system would be oriented in the following fashion. V2 would be positive to negative, right to left. V1 would be positive to negative, right to left. V4 would be positive to negative, left to right. And finally, V3 would be positive to negative, left to right. Even if you didn't take your time to realize conventional current would travel in this manner, just pick a direction and go with it and assign polarities as you think it would happen. The great thing about Kirchhoff's voltage law is as long as you stay consistent, you can't get it wrong. For the heck of it, let's start here and travel in the counterclockwise direction. We first go in source E3's negative and come out a positive. This would be considered a voltage rise. Let's put this on the left-hand side of the equation where all the rises go. We then travel through R2 in a positive and out a negative. This is a drop. Let's put this on the right-hand side of the equation where all the drops go. We then travel through source E2's negative and come out a positive. This is a voltage rise. Let's put this on the left-hand side of the equation where all the rises go. We then travel through R1 in a positive and out a negative. This is a voltage drop. Let's put this on the right-hand side of the equation where all the drops go. We then travel through source E1's positive and out a negative. This would be considered a voltage drop. Let's put this on the right-hand side of the equation where all the drops go. Again, we know source 1 really is an active 16-volt source. However, given our chosen direction of travel, in a positive, out a negative, we need to consider a voltage drop. We then travel through R4 in a positive and out a negative. This would be considered a voltage drop. Let's put this on the right-hand side of the equation where all the drops go. Finally, we travel through R3 in a positive and out a negative. This would be considered a voltage drop. Let's put this on the right-hand side of the equation where all the drops go. We're back where we started. The Kirchhoff's voltage law equation for this circuit is E2 plus E3 equals V2 plus V1 plus E1 plus V4 plus V3. Substituting in our known values for sources E1, E2, and E3, and then moving all the known values to one side demonstrates that V2 plus V1 plus V4 plus V3 equals 6 volts, implying that this multiple source series circuit could just as easily be simplified as a 6-volt source in series with 4 resistors. I leave it as an unguided exercise to the viewer to solve for current through and the voltage across each element in this simplification. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The 6-volt source in the simplification sees a total resistance of 220 ohms. Ohm's law demonstrates it would push 27.3 milliamperes of current counterclockwise through this system. Current through elements in series is the same. As a result, R1 experiences a 1.1 volt drop, R2 experiences a 1.9 volt drop, R3 experiences a 1.4 volt drop, and finally R4 experiences the remaining 1.6 volt drop. All we need to do is map these properties back to our original circuit and see if these results make sense. V1 is 1.1 volts, positive to negative, right to left. V2 is 1.9 volts, positive to negative, right to left. V3 is 1.4 volts, positive to negative, left to right. And finally, V4 is 1.6 volts, positive to negative, left to right. Let's check these results using Kirchhoff's voltage law to make sure we're tracking. Starting here and traveling counterclockwise, we encounter a 15-volt rise, followed by a 1.9 volt drop, followed by a 7-volt rise, followed by a 1.1 volt drop, followed by a 16 volt drop, followed by a 1.6 volt drop, followed by a 1.4 volt drop. 15 plus 7 does in fact equal 1.9 plus 1.1 plus 16 plus 1.6 plus 1.4. What came up did indeed go down. As I've mentioned before, as long as you stay consistent regarding polarity, you cannot get Kirchhoff's voltage law wrong. Just pick a direction and stick with it. For example, consider the circuit consisting of a series arrangement of unknown elements, which could be active sources, passive elements, or even boxes stuffed with dried leaves. We know nothing about what's inside each mystery box. The only thing we do know about them is that a voltmeter measuring the voltage across each element registers the following magnitudes and polarities. V1 is 4 volts, positive to negative, top to bottom. V2 is 8 volts, positive to negative, left to right. V3 is 12 volts, positive to negative, right to left. And finally, V2 is 2 volts, positive to negative, top to bottom. We know nothing about the fifth element, not its magnitude nor its polarity. However, we can use Kirchhoff's voltage law to determine both. Allow me to demonstrate. Kirchhoff's voltage law states that for any closed loop, the summation of voltage rises will be equal to the summation of voltage drops. Just pick a direction and stick with it. Seriously, pick any point on this loop and go in any direction. Just for the hell of it, I'm going to start here and go clockwise. What about the polarity markers for V5? Every other element has polarity markers, but not this guy. It's a total unknown. I'm just going to randomly assign it polarity markers positive to negative, left to right. Seriously, I just randomly picked these polarity markers. I don't know if this is correct or not, but I'm just going to go with it. If we chose correctly, the Kirchhoff's voltage law analysis will yield a positive value in the indicated direction. However, if we chose incorrectly, the Kirchhoff's voltage law analysis will yield a negative value in the indicated direction. It's then just a simple matter of assigning the correct polarity. Allow me to demonstrate. Starting here and traveling clockwise, we first encounter an 8 volt drop, followed by a 12 volt rise, followed by a 2 volt drop, followed by the unknown voltage rise across V5, followed by a 4 volt rise, and we're back where we started. All the rises on the left and all the drops on the right. Again, we don't know if V5 really is a drop or a rise. We just assign polarities randomly and remain consistent given our direction of travel. Moving all the known values to one side and solving for the unknown value V5 demonstrates V5 with the indicated polarity is negative 6 volts, implying V5 does have a 6 volt differential across it. However, it's not positive to negative, left to right as we initially suspected, but rather 6 volts positive to negative, right to left. Like I said, as long as you're consistent regarding polarity, you will get workable results with Kirchhoff's voltage law. If we were to open the box containing mystery element 5 and find a 30 ohm resistor under it, experiencing a 6 volt drop positive to negative, right to left, we could easily make the following assumptions about this circuit. Given R5, the 30 ohm resistor experiences a 6 volt differential across it, positive to negative, right to left. An application of Ohm's law demonstrates that 200 milliamperes of current must be flowing through this resistor, right to left. Current through elements in series is the same. Given the direction of current travel, unknown element 1 is undoubtedly a 4 volt source. Unknown element 2 is undoubtedly a passive resistor experiencing an 8 volt drop with 200 milliamperes of current through it. An application of Ohm's law demonstrates that R2 must be a 40 ohm resistor. Unknown element 3 is undoubtedly a 12 volt active source. And finally, unknown element 4 is undoubtedly a passive resistor experiencing 2 volt drop while 200 milliamperes of current travels through it. A final application of Ohm's law demonstrates that R4 must be 10 ohms. There you have it. A flurry of Ohm's law jabs and crosses and a Kirchhoff's voltage law uppercut has made this seemingly impossible problem readily solvable. I still have no idea what this circuit does. Seriously, half the goofy problems you'll find in a textbook seem purposely designed to frustrate and confuse first-year students rather than teach them something. This being said, as long as you travel a loop starting where you end, ending where you start, and remaining consistent regarding polarity as you travel the loop, Kirchhoff's voltage law is a reliable tactic for every circuit analysis scenario, regardless of complexity. We'll examine Kirchhoff's voltage law applied to parallel and series parallel circuits in later lectures. Before we bring this lecture to a close, let's do a quick demonstration of sources in a series aiding relationship. You recall the Tektronix CPS 250 triple output power supply we examined in the DC Power Supplies lecture, available at the Big Bad Tech channel, has a selector switch in the upper right-hand corner, allowing a user to choose between independent, series, and parallel mode. During the aforementioned lecture, we kept the power supply in independent mode, meaning adjustable sources A and B are electrically isolated from one another and they are independently adjustable. While in independent mode, an ohm meter demonstrates no connection exists between source B's positive terminal and source A's negative terminal. While in independent mode, a DC voltmeter demonstrates that source A is presently set to 12 volts. Similarly, while in independent mode, a DC voltmeter demonstrates that source B is presently set at 8 volts. In summary, in independent mode, these are two independent adjustable sources. If a user was to change the selector switch in the upper right-hand corner to series, the source closes a switch between the adjustable A and B source. You will note the closed switch stacks A on top of B, such that source B's positive terminal and source A's negative terminal are electrically connected in a series aiding relationship. With a power supply in series mode, an ohm meter demonstrates that these 2 points are now connected. Besides connecting the sources in series, the series mode also hands control of both sources over the source A voltage and current adjustment knobs. You recall that source A was presently set at 12 volts. With tracking handed over to the A source, both sources should now be at 12 volts. A DC voltmeter demonstrates that source A is 12 volts. Similarly, a DC voltmeter demonstrates that source B is also 12 volts. Given these sources are in a series aiding relationship, A on top of B, a DC voltmeter demonstrates that A's positive terminal is 12 plus 12, or 24 volts higher than source B's negative terminal. If we adjust the tracking input for source A up to 15 volts, the DC voltmeter demonstrates the series aiding relationship of A and B have a differential of 15 plus 15, or 30 volts. You note each adjustable output is limited to a max of 20 volts and 10 watts each. Configured in a series aiding fashion allows a combined output of up to 40 volts and 20 watts. Sources are often configured in a series aiding fashion to power a load together when one just wouldn't cut it. If only your lab partner could be equally as helpful. Alright, that's about it for today. In conclusion, this lecture took a look at DC voltage sources in series aiding and series opposing configurations. Additionally, we got some more practice with Kirchhoff's voltage law, and we took a look at a power supply in a series aiding configuration. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.